on the front. Okay, everybody. Wow, where is everybody? Anyway, so this is Shelby. She wants to talk to you about an opportunity. So if you want to stand here, the camera's right there. Let me see if I can take that. There you go.
Awesome, thank you. How are y'all today? Good. How are you? All four people here. Well, thank you for being here. My name is Shelby. I am the grant coordinator for Student Support Services. I graduated in December. How many of y'all know about Student Support Services? What it is? Awesome. Well, that's one. Okay, good. So we're an organization on campus. We're federally funded to support students who are first generation, low income, or registered to the Office of Disability Services. So if any of those things apply to you, you're eligible to apply. If you're a STEM major, you're eligible for the Student Support Services STEM. The main difference here is that we have STEM centered activities, and we also have a STEM scholarship. I believe last year everyone that applied got money to it. So definitely, I mean, a lot of problems with scholarships is that there's just not enough people applying to them. So definitely a good opportunity. We have early registration for if you're a member. We do success coaching. We do one-on-one tutoring. Our tutors have very flexible schedules, and we have tutors in a very vast variety of subjects. So whatever you need help with, we do. I think we did a CPR event last year. Just this weekend, we did a summit event. There was like free barbecue. You know, it was a good time. We had a really awesome keynote speaker. So we do all sorts of stuff to come, just kind of be more part on campus. It looks good on a resume. If you have classes that you're really strong in and you qualify as one of these three things, you can also be a tutor. I think the pay is $15 an hour part-time. I think up to 25 hours a week, depending on the need of students. So really awesome opportunities. Yeah, application.
Abigail is in the program, and she thinks it's great.
Awesome. Well, good. Thank you for being in the program. So yeah, if anyone, do any of y'all physically here want a little paper? Okay, sweet. I know Dr. Irvin has some in his office.
I have some in my office, but there's also a link to this flyer in our announcements. So go to announcements, it's the newest announcement, and click that link and you can download this flyer as well.
And this QR code is the general application. So if you're not a STEM major, you can still be in SSS, you're just in the traditional program, and you don't have access to that STEM scholarship. That's really the only difference. This application is a general application. It'll put you in both, and then when you have your STEM major, you'll get funneled into my area. And if you're one of these three things, you're going to get approved, and you'll have access to all the benefits. You'll be on the Canvas page for STEM, like SSS, and I know I send out scholarship announcements through there. So kind of save you having to search for them, right? Because there's a lot of obscure scholarships out there. So yeah, if y'all wanted paper, did anyone have any questions? No, did anyone online? If you have a question online, you can type it. Give a second, I'll give y'all the, do you want a paper?
We're up to 13 online, so. Yeah, again, if you want this, if you're at home, go to the Canvas page, look under announcements, and there should be an announcement with a button with a downloadable version of this, what you see on the screen. This is actually from the Canvas site. So. So right here. So look for the Student Support Services announcement under announcements. All right. Thank you very much, Shelby. By the way, she took organic from you. So you can survive the class. You can survive the class. So, all right. Stop sharing. And I'm going to start sharing my iPad. So let's see. Uh-oh. Got to plug it in. Okay. Let's see what's going to share. Okay. There's apparently an error on my slides. We're not taking the exams in June. We're taking them in May. So please. Okay. So this is, I'm going to start with, oh, there we go. I'm going to start with actually reviewing what's on Canvas for our next exam, which is May 2nd. Okay. Not this Monday, because today's this Monday. It's going to be the following Monday. Okay. Anyway, so then our final exam will be on the following Monday. So come prepared on Wednesday for our last quiz. pretty good turnout for people who turned in the extra bonus quiz. I was really happy with that. A lot of it. And I thought that was a really good, a primer for our next exam. So I think that's going to be good. So what I'm going to do is I'm going to talk about the next exam first, and then I'm going to go talk about the final. Okay. So, and again, these slides are on there. I think the only thing that's wrong with this is there's a couple things, the dates on here are wrong. But other than that, all the times and locations are correct. Okay, for chapter 8, again, this is on Canvas. You can look at under Canvas. It's called chapter 8 through 11 review. Okay, these are the top things that I want you to know. So chapter 8, addition reactions, right? So we went from our chapter 6, which was substitution reactions, chapter 7, which is elimination reactions, and now we're doing addition reactions. Okay, and so you need to know the 3 ways, which is substrate plus reagent equals what? Product and substrate, what's the reagent? And here's the product, here's the reagent. What did you start with? Know the reactions all 3 ways. Okay, and for the alcohol chapter 2, you should have close to 50 something, 55 reactions on your reaction table. So anybody counted? Anybody counted? Okay. So anyway, so that will kind of let you kind of get along. Know the difference between regio and stereochemistry of the reactions, right? We have the Markovnikov rule for one of the additions, but we learned we can mess that up. We can change that backwards in chapter 10. So make sure you know your Markovnikov rule and know the 3 different mechanisms. We're going to talk about those today, actually. So we're going to look at that as well. Know that you can make diols from osmium tetroxide and cold potassium permanganate. It's not actually on that sheet, but it's on the, it was on one of my exams. So I mean, no, never mind. It was on the quiz. That's what I meant. Know that you can cleave the double bonds with ozone, and that's the only way to make the aldehyde is to clip it with ozone and have a reducing environment. And then potassium permanganate will oxidize it down to carboxylic acids, always. And know the difference, know the reduction of, or the reactions of alkynes, specifically the reductions of alkynes with cis-trans stereoselectivity. The nickel boride and Landler's catalyst only give cis alkenes, and the dissolving metal reduction only gives trans alkenes. So you can be very careful about what you want to use. In fact, that's used a lot in multi-step synthesis because you'll have to have one or the other to do the next step. Okay, so that's the addition reactions. Remember, we have about 4 different types of mechanisms there. We have ones that form carbocations, and therefore you have mixed up stereochemistry and you have rearrangements. But then you have the kind that add across it and either make an intermediate, like the bromonium cation, and so that's an anti-addition. And then we have the mercury, which is an anti-addition, and then we have the boronation, deboronation, oxyboronation, where it's syn addition, backwards, where the boron's on the least substituted side. Okay, all right. Next chapter is spectroscopy. So there are 4 things you need to know about proton NMR: number of peaks, the integration of those peaks, the position of those peaks, and spin splitting. In carbon, it gets easier. You don't have splitting or integration, so it's just number of peaks and shift. Okay, and then the last thing is mass spec. Okay, we have 4 things to look for in mass spec, which are molecular ion peak. Remember, you're always going to have an M+1 that's 1% for the carbon-13. But then we want to look for our base peak, which is our tallest peak, our relative intensities of our different fragments. The base peak is your most stable fragment, the easiest fragment to get. And then the last thing is fragmentation pattern. Is it going 14, 14, 14, 14, 14, 14? Then that means it's a long straight chain and it's chopping off little bits all the way down. But the other thing we got to remember is that the nitrogen rule, which is if you have an odd parent ion peak, molecular ion peak, you have at least an odd number of nitrogens in your compound. Okay. Oh, can't see the PowerPoint. No, this isn't PowerPoint. This is a piece of paper that's on Canvas. I'll get to the PowerPoint after this. I just want to go over these topics first. Okay. All right. So then the other thing we got to remember is our M+2 peaks, specifically for things like bromine. Our M+2 peak is the same height as our M+1 peak. Chlorine, our M+2 peak is 1/3 the height, 25%. So those are things that we need to pay attention to. And that's spectroscopy. Okay, and the spectroscopy thing we did in class is going to be harder than what you'll see on the exam, but it gives you at least a good fighting chance. All right. Chapter 10, radicals. Okay, radicals can only do two things: abstract a hydrogen or add across a double bond. There are 3 steps to every radical reaction: initiation, propagation, and termination. How do you tell the difference between them? In initiation, you started with no radicals and you now have radicals. In propagation, you have radicals and you still have radicals. In termination, you have radicals and then you don't have radicals. Look at it that way. So if you look at the reaction, it's like, I don't know which step this is, use that tool. Okay, let's see. We need to look at peroxides. Peroxides are used to generate them because they have that weak bond. It makes it really easy to give you a homolytic cleavage. And so they each walk away with a radical. Reactivity and selectivity. Okay, reactivity and selectivity. So what is the more stable carbocation? I mean, the more stable radicals are faster. So your tertiary sites are faster than your secondary sites, and your secondary sites are faster than your primary sites. So if you look at the speed at which the radicals are abstracted, it has to do with the fact that the radical is more stable. The more stable radical, the faster that abstraction happens, and the faster the reaction goes. Now, when you have HBr and peroxides, you end up with an anti-Markovnikov's product. Okay, an anti-Markovnikov's product. But then we also talked about the allylic and benzylic radicals being more stable than even the tertiary radical. Okay, and we're going to go with that again. Okay, so that's radicals. Okay, actually, the raw average on the quiz was a 60. So that was really good. That's like the best raw score on a quiz so far. So that's great. Either I'm getting nicer or you're getting better. So let's hope that you're getting better. All right. So then our last chapter, alcohols. Again, we have every reaction we need for this thing, and your reaction table is going to help you next semester. So please keep those. Review your nomenclature. We're going to need it for the final anyway. We have alcohols and ethers for nomenclature. So, and review, go back to chapter 2 and review the thing about hydrogen bonding, boiling point, and water solubility. Okay, it's in the book, and we talked about it in chapter 2. I kind of, because we'd already talked about it in chapter 2, I didn't put it on the slides for this chapter, but go ahead and review that. Review the reactions for making alcohols. You know, adding water across a double bond, hydroboration, deboration, oxymercurization, demercurization. And remember, we can use all of those reactions to now make ethers. By doing them instead of water, you do them in alcohols. Let's see, reactions with HCl and HBr and HI. Okay, so we can get rid of that oxygen by protonating it, turning it into a good leaving group. And then in primaries, it's a substitution reaction. And in the secondaries and tertiaries, it's actually a carbocation. Then we also have another way of making oxygen a better leaving group. In fact, the rest of the chapter is almost making oxygen a better leaving group. We're making oxygen a better leaving group using phosphorus tribromide or thionyl chloride, SOCl2. We're turning it into a better leaving group, okay? And speaking of the sulfonate esters, the tosyl group. Now, we're gonna talk a little bit more about the tosyl group, but that's a good leaving group. Once you got that tosyl in there, it's as good a good leaving group as iodine. So it's great to have in your system. Williamson ether synthesis. And you know which way you wanna do it. You wanna try to have your alkyl halide be the lower, being primary, because that makes the reaction go faster, okay? And then the protecting groups. When you want to keep your alcohol, but you need to get away from that acidic proton for one step or more in a reaction. So we have that protection, deprotection. And we have the T-butyl ether, and we have the silyl ether. And the T-butyl ether clips off with acid and heat, but the silyl ether kicks off with fluoride ion. Very selective, very quick reaction. I mean, literally 10 minutes in room temperature stirring, boom, it's gone. It's a really cool reaction. And then epoxies. And again, in epoxies, we're making oxygen a better leaving group with ring strain. So we're using ring strain to help us there. Now, how do you make them? There's two ways. You can do the substitution ether reaction if you have a halohydrin. So that might be a good way to look for it on a multi-step reaction. Alkene, halohydrin, epoxy, boom. Or you can make it with the peracid, specifically metachloropurbenzoic acid. Know that acronym because a lot of times we'll just use MCPBA. So know the acronym there. And then the reactions, okay? There's two types of mechanisms in the reaction with the epoxies. There is the good nucleophile, where the nucleophile attacks the less substituted side. And then there's the acid catalyzed, where the nucleophile attacks the more substituted side. So know those two different mechanisms because they help you explain your regiochemistry. Okay, and that's chapter 11. Okay, any questions about any of those topics here or there? Okay, so I mean, it is good. We'll have a quiz on chapter 11 on Wednesday. We'll have the exam for, let's see, is it 5, 6, 7? No, it's just 8, 9, 10, and 11. It will be on Monday, the May 2nd, and then we'll have our final. All right, let's shift gears and talk. Yes.
What will we do on like, so we have the exam on Monday and then there's like a Wednesday before the.
No, that there's going to be that's reading day.
Oh, okay.
Yeah, that will be the last time we meet before the final.
Okay.
And the final must be live in person. There, or if you have ODS, you actually have to go get an assignment down to get extra time at the testing center. As long as you take it on Monday, that's fine. Okay. All right, so let's talk about the final exam. So it's the ACS final exam. It is on May 9th, Monday. I have a class before this and it's at 8 a.m. So if you wanted to take it early or something, there's an option. I just need to know ahead of time, so I'll have a booklet for you. And then there's the 2 o'clock. Ours is the 2 to 4:30. It's a standardized exam. You're supposed to have 110 minutes, but I think we're going to use the whole time. We'll see. Yes.
Like the orange ACS book?
No, that is undergrad. It's going to be a gray ACS book. The organic one is gray. So the Gen Chem one is, they have an orange one. So the book, the ACS practice booklet is the one that they're selling at the stockroom, and I think those are tan. So the practice booklet has all multiple, the exam has all multiple choice questions. You only have 4 choices. There's no E, and there's almost never none of the above, okay? There are 70 questions. You should answer all of them because we're probably going to end up with a 25-point curve anyway. And so every little question helps. The raw score on these are usually 50-ish. I had my honors class, actually, the class average was 56. So that was pretty good. So, but the class average for this is around 50. So, and I have some strategies for this, so don't forget that. So you're going to be given everything you need, and you cannot use a calculator. You have to use hand. In fact, at that, you'll need a photo ID. I'm going to check your photo ID when I hand them out and when you hand it back in. You're going to have to write your exam number on your Scantron. It's going to be one of the big ones, the big green ones. You got a bubble in your name and everything. And I'll show you that. And we're going to put your exam number on there so that I can track you forever. No, so just to make sure we don't have any of those walking away. Failure to turn in any of these things will have a 0. In fact, we're going to be no watches right there. We'll have a timer up front. All of your phones must be off and packed away. The only thing you can have out is pencils. And that's the only thing you can have on the desktop when I'm starting to hand out exams. Okay. Okay. Few helpful hints. Well, actually, I'll probably give you the whole 104 minutes, 140 minutes that we can use, unless I'm told I can only give it 110 minutes. Again, ODS, you get whatever you get, ODS. Make sure you understand the question. On this last exam, I warned people to read the question twice. Make sure you're going which way and what you're actually asking. Read all the possible answers first, and then figure out which one is there. Not only are you looking for the one you think is right, but you have a reason why the others are wrong. You know, John, yes, well, this one's pretty. You know, you don't want to do that. That's not a good way. Well, the one before it was A, so this one has to be B. So don't use any of that. Okay. So just try to figure out why the others are wrong. Make yourself a list of problems on your scratch paper that you want to go back to if you weren't sure. Things that you were sure of, just let it go. Bubble in as you go. There's no like time to bubble at the end. If you studied really hard and you don't recognize a reagent, it's probably not the right answer. If you didn't study hard, you're not going to recognize any of the reagents. So there you go. Okay. What follows is a summary of some of the concepts. So the rest of the slides are all about the summary from each chapter. You know, the big stuff. And so that you should all recognize these things, and that you should be, if you didn't recognize it, go back and study it a little bit, or things like going back and looking at some of the things that we're going to calculate. Okay, so what'll happen is I will get these to the testing center on Tuesday. They'll email me back an answer that same day, usually. And then I will open a bottle of scotch and try to figure out how to curve it. You know, it'll be a simple curve. It'll just be a plus X number of dots, so that it will not be another curve. So we'll just have that. And so it'll go on Canvas probably Wednesday. So I can, you know, see where I want to draw my A, B, and C lines. So right now, you know, based on whatever's happening on the next quiz, we're looking pretty good. Most of the homework is in. I'll finish grading that this week. But yeah, all the homework will be in on Wednesday. So I'll probably finish all of the homework stuff. And our quiz grade will probably be done on Thursday. And then we'll just have the one exam in the final. Yes. Oh, yes. I will bring them back. I will bring them on Wednesday. Because we actually have 7, 8, and 9. That I haven't given back yet. And so you'll get 7, 8, 9, and 10. So at least 8, 9, 10, because that's what's going to help you. And I've posted the keys for chapter 10 just today. So those are on there as well. Okay, questions before we begin a review? Okay. So I've harped on this a lot. Hybridization controls shape, shape controls hybridization. Right? You need to make sure you understand that hybridization is why we have our shapes. And lone pairs gives us our molecular shape, but bonds give us our molecular shape, and lone pairs help shape that. So we need to pay attention to that. Knowing our Lewis dot structures. I'm constantly drawing in that lone pair to make sure we remember there, okay? Knowing the formal charge, being able to calculate formal charge. And that is equal to the valence electrons minus the non-bonding or lone pair electrons, or in the case of a radical, an unpaired electron, and half of the bonding electrons, because it's sharing those. So you get half of the bonding. So don't forget how to do that formal charge calculation. Okay. It's a good thing to remember how many bonds something has in its normal state. Hydrogen only has 1, halogens only have 1. Oxygens have 2 and 2 lone pairs. Nitrogen have 3 and 1 lone pair. Carbon has 4 and no lone pairs. So those will help you kind of get draw a Lewis dot structure of something you've never seen before. You can probably use that strategy to help you start. Given a molecular formula or name, predict the hybridization and bond angles. What's this bond angle? Well, it's tetrahedral. I know what it is. It's trigonal planar. I know what it is. It's linear. I know what it is. Okay. Questions on that? So now that we've actually gone all the way through radicals and anions, let's talk about the similarities and differences between different shapes. Our carbocation is sp2 hybridized, trigonal planar with an empty unhybridized p, 0 electrons. That's where we get the cation. And that's why we get our selectivity of racemizing our thing, because our nucleophile can come from the top or bottom. The radical is very similar. It's sp2 hybridized, trigonal planar, and there's 1 electron in the p orbital. Spends half its time on the top, half its time on the bottom. So it's nice and easy to react. But look at this. When we have the methyl anion, we have 2 electrons, so it can fill an orbital. Okay, so now we have a total of 8 electrons around that carbon, and we have an anion. And it's sp3 hybridized. Because it can fill its octet, it's going to go to the hybridized state. Okay. So shapes of molecular shapes change with the number of lone pairs you have. 2 lone pairs on oxygen makes it bent. But on our nitrogen, we only have 1 lone pair. So that's trigonal pyramidal. But if we put another hydrogen on there and turn it into a plus charge, we go to tetrahedral. Notice it's the same, they're all sp3s. It's just having that extra lone pair. All right. Question so far? Okay. So, and now, you know, we didn't do this originally because you hadn't done the anions or the cations yet, but we have those, we've done those now. So the different ways to represent a chemical structure: condensed form, written out as numbers and letters; the Lewis dot structure, which is really helpful to figure out what's going to react with what; our skeletal structure right here. So condensed structures, Lewis dot structures, skeletal structures. And if we want to know our stereochemistry, we have to do our perspective formulas like this right here. Okay. And know what your dashed wedges and solid wedges mean. We don't really use the ball and stick very much, other than just to kind of, come on. There we go. We don't use that very much, but we do use a lot of Newman and Fischer projections. Newman projection is going to tell us how, where the big groups are and how easy it is to rotate. Our Fischer projections are for chiral stuff, specifically diastereomers. It makes it really easy to draw all your isomers with diastereomers using your Fischer projection. Okay, so don't forget how to draw those different projections. Okay, so in chapter 1, we also talked about resonance and resonance structures. So when you have 2 or more valid Lewis dot structures, then you have a resonance hybrid made out of them. So anytime you have delocalized electrons is when they're shared over 3 or more atoms. Okay, think about the acetate ion, where the negative charge is going from one oxygen to the next. It's shared over 3 atoms, and we have a resonance hybrid for that. The resonance hybrid shows the delocalization. So if you look at here, you have a partially negative charge on this atom, partially negative charge on that atom, and partial double bonds here and here. So we're showing those as where you're. And then each of these individual resonance structures is contributing to that resonance hybrid, but they're not all equal. For example, the negative charge is usually going to be on the more on the more electronegative atom, which means it's going to spend a little more time in the A configuration here. I'm sorry, the B configuration, because oxygen is more electrophilic or electronegative, more electronegative than nitrogen. So it's going to spend a little more time there. Okay, so you're going to see that as the major contributor to the resonance hybrid. And then we look at delocalization energy. Why do we do this? It helps whenever you spread your charge out. It makes things more acidic. It makes things easier to form. It makes things easier to react. Okay, and remember, we also have this delocalization when we have radicals. We have allylic and benzylic radicals, and we have allylic and benzylic carbocations. And those have these resonance hybrid structures. Okay. So when we're talking about stability, we want to see if the atom has an incomplete octet, it's not very stable. So that's going to be a lower contributor. The negative charge should be on the most electronegative atom. And positive charge should be on the least electronegative atom. And then charge separation. The further two charges apart, the less of a configuration, the less of it being a resonance contributor. It's not as good a resonance contributor. So if we look at these right here, we have, they're in conjugation, everything has an octet. So this is going to be the most stable resonance contributor. So it's going to contribute most. But if we kick some electrons in, we have a negative charge on a carbon and a positive charge on oxygen. That's backwards from the thing I just set up before. So this is going to be not very stable, okay? But we can flip the electrons the other way, have the negative charge on the more electronegative atom, the positive charge on the less electronegative atom. And so this is going to be a better contributor than E, but not as good a contributor as F. So F is going to be the major contributor, G is going to be a minor contributor, and E is going to be the least contributing. Okay, remember that stability trend. All right. So that's all of chapter 1. Okay. So now if you actually go back and review chapter 1 with everything you've learned, you're going to go, oh, wow, I remember all that now. So it's going to be good. We've learned a lot. We've done a lot. We have a lot on our reaction tables, and we're gonna keep it all in our heads until we take the second half. Okay, so know the functional groups on the table in chapter 2. Number 1, you're going to need them for nomenclature. In fact, you might want to look at some of the nomenclature. There's a nomenclature review that has all those functional groups and their priorities. Okay, understand electronegativity and polarity. Okay. Know how to trend it on the chart here. And then look at these intermolecular interactions, okay? Our intramolecular interactions are the bonds and the ions, okay? Those are within the molecule, but now we have to look outside the molecule. And we have those dipole, induced dipole, and hydrogen bonding. Induced dipole is the weakest, followed by dipole, and hydrogen bonding is the strongest, and therefore it'll have the highest effect on melting point, boiling point, and solubility. Okay, know which functional groups give rise to which types of interactions. Ketones and aldehydes only have dipole. Hydrocarbons only have induced dipole. Alcohols have hydrogen bonding. Amines have hydrogen bonding, so you'll want to see that. And then the more molecular interactions you have, or the stronger the molecular interactions you have, the greater it's going to affect your melting point. And it always goes up. The more interactions, the higher the boiling point and melting point. Okay. So again, in chapter 11, I didn't go over water solubility and stuff because we'd already done it in chapter 2. So you might want to review that before our exam. Things to affect your boiling point and melting point is number 1, molecular weight. As things get bigger, they boil higher. Number 2, hydrogen bonding. That's going to really, really affect it. Okay, is it polar or not? Because that's going to give you the dipole interaction, which isn't as strong as hydrogen bonding, but it's okay. And then, is it branched? A branched hydrocarbon has less of an ability to lay down next to other and induce a dipole. So it has fewer interactions if it's a ball. It only touches on a couple places, and it's trying to induce dipoles in several different places at once. And so it can't do that. So that's looking for it. And we can also, by lowering the pressure, you can actually make things boil at lower pressures. So you pull a vacuum on something and you can get something that only boils at 200 to boil at 50 degrees. So let's look at that in a little bit here. What we're going to do on this one is we have alkanes. They only have the induced dipole. And so for molecular weight, they're going to have the lowest boiling points, okay? But look what the effect of is just adding 1 carbon right here. We get about a 40-degree boss just by adding a carbon. So molecular weight is first, and then the types of interactions is second. Well, we go from something that's about the same weight here, but we add a polar group now, and it jumps up again about 20 degrees. And then by adding a carbon, it jumps up another 30 degrees. Okay, let's add something that moderately hydrogen bonds. Wow, it jumps up another 30 degrees. And then again, we jump up 1 carbon, it goes up another 30 degrees. And then we have alcohols, which have a stronger hydrogen bonding, highest yet, and again, adding a carbon. Okay. So things that we should see here are that trend of molecular weight and type of interactions, strong interactions. So increasing molecular weight, branching decreases melting point, and then you learned in lab from a mixed melting point experiment that impurities decrease melting point. Okay, so for solubility, think like dissolves like. Polar compounds dissolve polar compounds, nonpolar compounds dissolve nonpolar compounds. And you want to have, so if it's just one group. If you have 2 groups on you, like an alcohol, you have a nonpolar part of it, and then you have the hydrogen bonding part of it. Turns out one alcohol can pull, one OH group can pull in about 4 carbons to make it soluble in water. That 5th carbon, it's very poorly soluble, the pentanol. But guess what? If you have 8 carbons and you put 2 hydroxyls on there, that's going to be water soluble again. So it's 4 carbons per hydroxyl. Okay. Ethers, about 3 of the carbons will be soluble in water because it's a less strong interaction. Amines, primaries and secondaries are more soluble than tertiaries. Why? Primary has 2 hydrogens to hydrogen bond. Secondary has 1 hydrogen-hydrogen bond. The tertiary has 0 hydrogens to hydrogen bond. So that's why the solubility changes. Okay. And then alkyl halides, turns out fluorine can hydrogen bond as well. And so alkyl fluorides can be water soluble, but most of the alkyl halides are not, the other alkyl halides. Okay, remember this in the solubility thing right here, we also want to remember our polar aproducts and our polar products. Okay. Okay, so that's chapter 2. And I would definitely review the solubility thing for this next exam. Okay, acids and bases. So know the difference between pKa, pH, and pK. pK is our equilibrium constant. I'm sorry, Ka is our equilibrium constant. pKa is the log of it, which gives us our nice numbers right here. Know this trend on this table here. Carboxylic acids have delocalization, and therefore they're most acidic. Phenols have conjugation with the benzene ring, so they're more acidic, but less acidic than carboxylic acids. Then we have alcohols, alkynes, amines, alkenes, and alkanes being our least acidic right here. Why are alkanes least acidic? Because of hybridization. Okay, we have sp. Oh, over here. sp3 right here has 1/3 S character, 25% S character, 33% S character, 50% S character. It holds it tighter. It holds the charge tighter in because it's the S bond, and therefore it makes it more acidic because it can support that charge better. Okay. Know that adding electronic drawing groups will make things more acidic. In fact, we did that by looking at that inductive effect, right? Electron donating things make things less acidic. We didn't really do much with that, but we saw that. And resonance stabilization makes things more acidic. So there are 4 things that we need to worry about with acidity. The first one is electronegativity, but balance it with size. Electronegativity and size. That's why iodine, Hi, is more acidic than HBr because of its size. Okay. Hybridization, sp2, sp3, sp. Resonance, which is more charge you can spread out over more places, the easier it is. And then the inductive effects. That's the through bond effects. Okay. Electronegativity affects the polarity. It affects the acidity or basicity of a system, and it affects the ability to leave. The better of the worse, the weaker the base, the better the leaving group. The weaker the base, the better the leaving. Okay, and its trends. All right. So we learned nomenclature in 4, 6, 7, 8, and again in 11. So go ahead and review your nomenclature for alkanes, alkenes, alkynes, cyclic compounds, alkyl halides, alcohols, ethers, and epoxides. Remember, there's 2 ways to do that. You oxirane, and you number it differently if you use oxirane versus epoxy. If you use epoxy, you don't start at the oxygen. If you use oxirane, you start at the oxygen. And then your R and S and E and Z and cis and trans. Okay. And again, our priority assignments, they're technically 4. 1 is atomic number. 2 is, you keep going out until the difference. 3 is double bonds and triple bonds. What each of those bonds counts for that thing it's bonded to. And then of course, 4th one is isotope. All right. Overview of nomenclature. Again, there's a nomenclature review under resources, and it's several pages long. It gives you the alkyl groups and all that stuff. But now I'm adding a statement in my number 1 thing to do is longest parent hydrocarbon group containing the highest priority functional group. Okay, that's where this comes in. The priority list is on that review. So please take that with you. List substituents alphabetically, not alphabetizing di, tri, tert, or sec. But you do iso. And here's the way to remember that. Okay, let's look at our substituents here. Isobutyl is all one word. So you use the alphabetization. Sec is hyphenated. So you don't, you use the B. That's how to remember that. Okay. All the rest of them, you know, the tert butyl here and the sec butyl here are with the B. Isobutyl is with the I. And so remember that little rule. And of course, lowest number, etc. Okay. Now, do I do, that's rings. Okay. Also, don't forget, when numbering alkenes, even if you have an alcohol on there, both of the carbons of the alkene have to appear in the parent. Okay, both of the carbons in an alkene or an alkyne have to be in your parent, even if the alcohol is changing the group. That ene all rule and ine all rule too. Okay. Okay, let's see. In rings, you want to try to have one of the substituents be on number 1. If you only have 1 substituent, it's always number 1. But then you want to have the lowest number possible. But that rule breaks down when you have an alkene. Because in an alkene, a cycloalkene, you must have carbons 1 and 2 be the alkene carbons first. Okay, so in the case of here, we have to call this one 1 because it has a substituent, which means this one has to be 2. So this is 3, 4, 5, and 6. So it's actually, that chloro is on 6. So that's 1,6-dichlorocyclohexene. So that, see, that's the tricky one here. Yeah. And that's why you have to have, and so again, this is number 1 because it has a substituent, which makes this carbon number 2, which makes this one number 5. So that's a tricky one. The regular cyclic one's not hard, but that one's tricky. Okay, bicyclos. Okay, remember your bicycle rules. It's all the carbons in both of the cycles, and that's your parent. Use the word bicycle in brackets. Don't forget that it's easy to start with your bridgehead columns and just go with your brackets. Bracket says 3, you go 3 carbons. Bracket says 2, you go 2 carbons. Bracket says 1, you go 1 carbon. Bracket says 0, you go 0 carbons. So that should be easy, and well, that should be a good thing to remember. And don't forget that these are your bridges, and you start numbering at your bridge head. You start numbering at your bridge head, go around the biggest ring first, the second ring, and then the third one. So you go in order. All right, questions on bicyclos? Okay. All right, and then degrees of unsaturation. Yes.
I have a question.
Yes.
On the bicycle. So the bridgehead is like the middle, right?
The bridgehead is, the bridgehead carbons are going to be the ones that all the bridges come to.
Oh, so like the joints? kind of?
Well, it's going to be well, yeah, I guess it's the joints. It's usually the one that's substituted 3 times.
Okay, so then do you count like the example there where it connects the middle?
Mhm.
Is that like, would that be the last carbon?
This is the last bridge.
Okay,
So this would be, let's say, we're going to start numbering here 1, 2, 3, 4, 5, 6, and then that would be 7.
oh, so you just have to like go to the.
Right. That's you should be able to follow all of them, but the last bridge.
Okay.
Okay. And then of course our bridge here is a 0. So you have 1.1.0 for that one. Okay. And remember, when numbering your bridgeheads like this, you start at a bridgehead, and that'll help you figure out where your substituent is. Okay, degrees of unsaturation. You must be able to do that, where 2n plus 2 minus 2x, all right, is equal to the number of hydrogens you have, right here. And n is the number of carbons, x is the number you're searching for. So you only have one variable there, and it's x. And it's going to be a whole number. It's not going to be half a number, it's going to be a whole number. So what we're looking for is that. Another way to look at it is if they give you a structure and they say, what are my degrees of unsaturation? You add up all the rings and all the double bonds, or all the pi bonds. So we have a ring, so that's 1. We have a pi bond and another pi bond, so this is going to be 3. And so then you can go back and calculate that to make sure, to double check. But that's one way to do it fast if they show you the structure. If they just give you the empirical formula, you have to do the calculation. So remember that 2n, where n is the number of carbons, x is what you're looking for, and then this is going to be the number of hydrogens in your empirical formula. Now, if you have an oxygen, don't worry about it. It bonds twice, so it doesn't affect the calculation. If you have a halogen, it counts as a hydrogen because it only bonds once. So the bromine here actually counts as a hydrogen, so we have a total of 12 hydrogens. Then we're looking for our unsaturation. If you have nitrogen, you have to subtract 1 because it bonds 3 times. And so that way you can do any crazy combination of atoms and still come up with that. So in this case here, we have a C6. We have 3 halogens and 1 of those. So that's going to be 13 minus 1 for the nitrogen is 12. It's going to be effectively 12 hydrogens. Plug that into your 2n plus 2 minus 2x equation. And you'll use 12 on this side and 6 on this side. All right, so again, you won't need that for this exam, but you'll definitely need it for the final. Okay, good. All right, so cyclohexane things to remember. You have 2 primary configurations, chair 1 and chair 2. The chair that is the most stable is the one where the largest group is equatorial. Flipping from chair 1 to chair 2, all the axial hydrogens in chair 1 turn into equatorial hydrogens in chair 2, and vice versa. Okay, so that means that when we look for those, the most stable configuration, we're looking for putting the smallest groups in the axial positions and the biggest groups on the equatorial positions. So if you have competition, you'll know exactly which way. You know, and the question is like, which of these 2 chairs is most stable? Okay, chapter 5, the dreaded chirality. Back with a vengeance. So know your R's and S's and your priorities like that. Again, count for 4 different groups. That works really well if you only have 1 stereocenter. If you have 2 stereocenters, you got to watch out because of meso compounds. Okay. Enantiomers are the non-superposable pairs. We only have 2 of those. Diastereomers are sets based on how many chiral centers you have. And it's 2 to the n. So if you have 2 chiral centers, you should have a total of 4 compounds, unless one of them's meso. Then you'll have 3. If it's 3 stereocenters, you're going to have 8 isomers. Hope that's not an exam. That'd be horrible. And again, we use this Fischer projection here to make it easier to draw them. Notice that we have a mirror plane here. So that means that these are enantiomers. And then if we just swap one of these, we get to the other set, and these are enantiomers. But that means these are diastereomers, these are diastereomers, this is a diastereomer. So our diastereomers are from one set of enantiomers compared to the other set of enantiomers. Okay. And then, of course, our dreaded mirror planes on meso compound. Make sure that you either do it in your head, rotate it around to make sure that see if it's a mirror plane or not, or redraw it. Redrawing it helps, you'll have scratch paper. Okay, now our Fischer projections. Remember that you want your longest chain, your carbon chain, to be vertical. And that means they're going backwards into the paper. The stuff that's horizontal is coming out at you. So when you translate it from stereo to Fischer, you want to make sure you do it that way. Or when you go Fischer to stereo, you want to make sure you do it that way. And again, the Fischer makes it really easy to find mirror planes and all that kind of stuff. Okay. R and S use those same rules we use for E and Z. And then we're going to want to get our lowest priority. You have to get all 4 prioritized, and our lowest priority has to be away from us. And clockwise is R, and counterclockwise is S. You might want to remember or practice a couple of those. I think I still have the chiral activity and the chiral activity key still posted, so you can use that for practice. Okay, so that is the dreaded chapter 5. R. So let's go on to thermodynamics and kinetics. Okay, kinetics is how fast something happened. Okay, it doesn't matter how much energy it took. It's just done fast. Thermodynamics doesn't matter which path you take. All it matters is the beginning and the end. Okay, so thermodynamics is this and this. However high this barrier is controls your kinetics. Higher the barrier, the slower the reaction. Okay, so you want to make sure you do that. You want to know what the rate determining step is. It's usually the one with the highest activation rate. It's usually the first one too. And you need to know the difference between transition state and intermediate. Transition state is at the top of your humps. Intermediates are high energy materials in between humps, and products are down here. If you have a negative delta G or delta H, you're exothermic. Your reaction is favored. And if it's up here, the reaction is less favored, but it's endothermic. It absorbs heat to make that product. Okay, let's see. And just recognize your reaction diagrams. You can recognize them by mechanism. Sn1 E1 has a 2 hump. Sn2 E2 has 1 hump. So that makes it really easy. Orders of reactions. So if in a first order reaction, you only have one little 1 here. And so that's a first order reaction. This has basically 1 plus 1 is equal to 2, making it a second order reaction. Okay, so let's talk about all of our reactions and see how they fit into this first and second rate order. Only Sn1 and E1 form that carbocation intermediate, and therefore it only cares about breaking that bond. Remember, there's only 4 things that can happen in a mechanism. No, 5 things that can happen in a mechanism. Add a proton, take a proton away, react a nucleophile with an electrophile, rearrange, or break to form a stable fragment or molecule. Okay, so in the Sn1 and E1, we're breaking one of those 5 things that can happen in a mechanism. And therefore, it just waits around until it breaks that bond, and then it's a reactive intermediate and it reacts quickly. All right, let's look at our second order reaction. In Sn2, they both had to be at the same place at the same time, right? In E2, you had to be pulling on the proton while the leaving group was leaving. And they had to be anti-periplanar to each other to leave. And look at this, the radical reactions, The first propagation step is the rate determining step because you have to have the radical initiator and your substrate at the same time. So that makes it a second order reaction. Okay, so that's pretty cool. So we're kind of bringing in all of our chapters together. Okay. All right. Stability. Carbocation stability. So our tertiary carbocation is our most stable, followed closely by our benzylic and our vinylic. Okay, and I'm sorry, allylic, because of resonance stabilization. But the tertiary is still has more coordination, and therefore it's still more stable. Then, of course, secondary, primary methyl vinyl, which we hardly ever see primary methyl or vinyl. Only in mass spec do we see this. Okay, and the dreaded thing about carbocations is that a secondary will always rearrange to a tertiary, and it only goes two ways. It either, no, that's not true. It goes three ways. Hydrogen, hydride shift, 1,2 hydride shift, 1,2 methyl shift, or ring expansion. Okay. If you have a 3, 4, or 5-membered ring, you have ring strain. And ring strain is a driving force to go from a secondary carbocation to expanding a ring to give you a tertiary carbocation. Okay. So in the case of this one right here, we had water leave, giving us a carbocation here. We have a 5-membered ring that has ring strain. So we're going to do technically a methyl shift, but it's a ring expansion because we're not having a methyl group there, and giving us the tertiary carbocation. And then, of course, giving us our final product. Okay, so ring expansion because of ring strain. Okay. Things you should know about Sn1 and Sn2 are the rate, and they are favored by polar protic solvents. In fact, they're also favored by weak nucleophiles, which include water, methanol, and acetic acid, which are all polar protic solvents. Okay, they can support both cations and anions. Okay, they can support both cations and anions, and so that's going to give us a trend. In Sn2 reactions, you have a good nucleophile. Okay, you have a good nucleophile. And then don't forget leaving group effects. The bigger, more polarizable, or the weaker the base, the better the leaving group. That's why iodine's a great leaving group. And we have a new leaving group we just learned about in our alcohol chapter. It's the OTS. Oops, the tosyl. OTS. There we go. This is as good a leaving group as iodine. So it's a great leaving group. And so converting that to a better leaving group is important. Okay. So compare and contrast. Sn2, primary, secondary are faster than tertiaries. Tertiaries are really hard to do. It's a one-step reaction, which means you have one hump. No carbocation rearrangements, and you have inversion of stereocenters. Inversion of stereocenters. Sn1, we form a carbocation, so then it's going to rearrange. We get a mixed stereochemistry because it can attack the top or the bottom. And tertiary is much faster than secondary, and primaries and methyls don't really do it, except in mass spec. So what do we mean by good nucleophiles? There's actually a table in the book, I think, that has good nucleophiles, fair nucleophiles, and poor nucleophiles. So most of the good nucleophiles are going to have a negative charge. Okay, most of the good nucleophiles are going to have a negative charge, and so they're easy to find. And we don't really usually care about the spectator ion, whether it was sodium or potassium, but every once in a while they'll come up with it. The neutral ones, actually, I'll show it on there. The neutral ones are the poor ones, harder, the poorer nucleophiles or fair nucleophiles. But remember, our nucleophiles change in our solvents, specifically our halogens. Okay, because the polar protic solvents can support anions and cations, it changes there. So that makes iodine more nucleophilic in a protic solvent because it's the protic solvent making it the more acidic. So it's going to make it the better one. But in aprotic solvents, fluorine, that anion can't be supported by the dipole-dipole or the dipole-ion interaction, and therefore it's more nucleophilic. So think of it that way. So we have this is the better one for here. This is the better one for there. So remember that solvent effect. Okay. Probably aren't going to have to worry about the spectator ions here. We usually omit them, but they're there. The other cool thing about this is that negatively charged nucleophiles yield neutral products. Neutral nucleophiles yield charged products, and then you have to remove a proton. So if you just have your standard separation here, you go like this, and you form the weaker base. In this case, the bromide ion is the weaker base than hydroxide ion, and we form the weaker base. In the case here, we'll end up with a protonated intermediate here. And in this case, we're using the nucleophile as the base, our poor nucleophile as the base, and gets us to our neutral product after a proton transfer. So that's cool. Negative charge in, negative charge out, neutral molecule. No charge. When it forms, it charges, giving us a proton, an acidic proton that we then have to get rid of. Okay. All right. Are we still? Yeah, time. Good. Okay. So what do we need to know about E1, E2? Well, know the mechanism. E1 forms a carbocation, can rearrange. E2 does not. We have a rule for this, the Zaitsev rule. It's always going to form the more stable one if it can. But if you have a big bulky base, you're going to get Hoffman rule, the Hoffman product, which is not the safest, but not the most stable, but the one that's easiest to get to for the big bulky base. And again, stabilities go with the more substituted it is, the more stable it is. Okay. For secondaries and tertiary reaction halides, E2 is favored at higher concentrations of strong bases in polar aprotics. E1s are favored in polar protic solvents with weak bases. In fact, water is a weak base. That's a polar protic solvent. Methanol is a weak base, polar protic solvent. Primaries can only do an E2. They can't form a carbocation, so it can only do E2. And so you might want to get that table out again, the empty one, and try to fill it in. There. The other weird thing is that the hydrogen must be coplanar, or actually antiplanar, with your leaving group. So in cyclohexanes, we might not be able to do elimination at all. But your halogen has to be in an axial position, and a hydrogen has to be in an axial position. That's the only way it can form it. And if you can't do that, if it's blocked, then you can't do a reaction. For example, here we have a methyl group in the axial, in the axial position. And so this one won't eliminate. So no reaction can be the right answer. Okay. So again, work yourself through these tables. Again, big bases only do E2. Now, methoxide is small enough to act as a nucleophile on primary unhindered, but it's going to eliminate everywhere else. Substitution everywhere except for the tertiaries because of the sterics, the crowding. And then this one does weak base, weak nucleophile has to form the carbocation. And the secondaries don't form very fast, so it's a really slow reaction. Okay, so what's strong nucleophiles? Look at all these strong nucleophiles. All charged. Okay, and weak nucleophiles, all of them are iodine and fluorine can be on this list depending on your solvent as weak nucleophiles because they're very weak bases. They're great leaving groups, so they're very weak bases. All right, so that was chapter 6. And then we learned a lot of cool reactions in chapter 7. We learned a lot of ways to go converting from one to the other. So here we know we can take our alcohol and do a dehydration with either of these two reagents and actually get to our alkene, right? So that's one way to get to an alkene. But the other way is to do a dehydrohalogenation. Okay, so this would be a great thing for in a multi-step synthesis, saying I want a bromocyclohexane or I want a chlorocyclohexane. How am I going to get that? Well, I'm going to take cyclohexane and do a radical reaction. And then I can turn it into a substituted reaction. If I have a good nucleophile, I can get substitution. Or if I have a good base, I can get to an alkene. So I can start from cyclohexane and get to cyclohexene in just 2 steps. So think about having your reactions in multi-step syntheses as well. And this is what we also learned in this chapter. This tosyl group makes a good leaving group. Okay, take that OH, turn it into a good leaving group, and it will either be displaced by a good nucleophile or turns or be eliminated in an E2 reaction. Okay, so in the dehydration of secondary and tertiaries, it goes through an E1 mechanism because you can form a secondary or tertiary carbocation. But that doesn't work with the primary. Primary has to do it where you actually protonate the species and then the water has to come and act as the base. It's an E2 because you can't form the primary carbocation. All right, so chapter 8, we added stuff across our double bonds, okay? In this case, our double bond is the nucleophile. The p orbital, the 2 electrons in that p orbital, are the nucleophile. And then we get change in hybridization. Okay, so when we add HBr or HI or HCl across it, the slow step is the addition of the hydrogen. And remember Markovnikov's rule. It adds against the hydrogen because you want the hydrogen on the one with more hydrogen. So it's going to add to the side with the more hydrogen. And then that means your halide is going to be on the other side. So that's a pretty quick and mechanism, and it's similar to the hydrohalogenation. No, it's similar to the dehydration or the hydration. Hydration and hydrohalogenation are the same mechanism, and give you a mixture of syn and anti because you form the carbocation. Okay. In the case of halogenation, you always get anti-addition because you form this one up here, and the halide has to come on and attack one of the 2 sides on the bottom. So it'll always give a trans product. What if you wanted a cis product? Well, you would want to do some other reaction. That's not going to work. Okay, stereochemistry. Okay, depending on where you have it, you're always going to get anti-addition, but which kind of isomers you get depends on where you're starting with. Here we have 1 substitution. So that means the bromine can attack at the bottom here or on this side here, and it actually will give us 1 of 2 enantiomers possible. So we only have 1 stereocenter right here, and we're going to see that it's going to give us 1 stereocenter, and we can get it of the 2 enantiomers, because if you made the bridge on the bottom here, that's going to put the R group out here. So we see that. In the case of starting with the trans alkene right here, if we attack from the top, we get the 1 isomer, but then if we attack from the bottom, we get another isomer, but we have a meso compound. If you rotate it around such that the 2 bromines are together, we see it's a meso compound. And if we attack at the top, we get 1 isomer. If we attack at the bottom first, we get the other isomer, and we end up with a mixture of enantiomers. So it is selective. However, whichever side you come onto, it's going to be anti-addition. But if you start at the top, it's going to give one enantiomer. Start at the bottom, it's going to give the other enantiomer. Okay. And then, of course, this alkene. We added 2 new reactions to this alkene in the alcohols chapter. We learned how to make the alcohols before, but then we added the esterifications. Okay, we can do that with the acid catalyzed hydration. All we do is remove the water and add an alcohol. Okay, and we can do it with oxymercurization because the mercury is going to be here, and then we have attack by the nucleophile over here. And that, in the case of this one here, it's water, but we replace water with an alcohol, and we'll have attack by that nucleophile at that site. And it's great because you get a secondary ether or a secondary alcohol with no rearrangement. And then, of course, our last one is boron. Here, you cannot make an ether with this one because you're going to put the boron here, and then you actually are oxidizing this boron carbon bond, and that's where the OH comes in, with that oxidized material. All right. Okay, yeah, that's it. So again, this is where knowing the reagent, the product, and the starting material, and being able to do it all three ways is going to be really, really important. So on Wednesday after the quiz, I'm going to finish up this right here, and then I'm going to do another multi-step synthesis experiment. Okay, fine. No, we have a couple minutes. I'm going to keep going. All right. Then we have all of these reactions. Know how to do what they have. Like you have a mixture of syn and anti because of carbocation. You have a mixture of syn and anti because of carbocation. You have anti because you're blocking the top. Halohydrin reaction is anti because you're blocking the top and you just have water. Or an alcohol will make it an ether as well. Boron, it's a syn addition, happens all at once. The oxymercurization is it can look syn or anti depending on which side it started on, but it always gives that regiospecific. We can break it if you want to break your double bond. You can do it with ozone if you want aldehydes, or hot permanganate if you want carboxylic acid. And for diols, 1,2 diols, you have osmium tetroxide, or cold permanganate. That was on our quiz, that one there as well. So kind of know the selectivity and regioselectivity. Okay, alkynes. Okay, we know that the alkynes react like the alkenes. It's just you have 2 pi bonds to play with. So if you have one equivalent, you can add one equivalent across it and you still have a double bond. But, oh, we're making them first. Oh, how do you make them? You have to have 2 equivalents of acid to remove. And there's 2 ways to do that. You can have a geminal dichloride, or you can have a vicinal dihalogen right here. As long as there's hydrogens on each of those carbons, you can still remove both of them. And hydroxide is not strong enough. We must use sodium amide. So if you ever see sodium amide there, it's got something to do with acetylene. Either you're making the acetylide proton or you're making acetylene. Okay, so how would we make a geminal dichloride? We have a reaction with POCl5. It makes a geminal dichloride out of a ketone. Okay, how do we make the vicinal dibromide? Add bromine across a double bond. So think about that as a multi-step synthesis. Cyclohexene, or you have hexene, 3-hexene. You add bromine across it. You add 2 equivalents of base, and you have hexine, 3-hexine. Okay. And then we have electrophilic addition. Okay, in electrophilic addition, you actually have the electrons from the pi bond reaching out to grab a hydrogen, and then that generates a carbocation, which then gets attacked by the nucleophile. So let's see. All right, a couple more alkyne reactions. I think I'm gonna finish the alkyne reactions and then I'm gonna stop for today. Okay, let's see. So right here, again, with these reactions, one equivalent stops. Second equivalent gives you a geminal dihalide because it's adding Markovnikov. You added a hydrogen, so that's directing it now. That hydrogen is saying, I'm gonna add the other hydrogen here at the same place and giving the, so it's our Markovnikov's addition. If you want a trans vicinal, you can give one equivalent of bromine to get the trans, or one equivalent of chlorine. Or if you want the tetrabromo or tetrachloro, add a second equivalent. All right, and okay, no, I'm gonna stop here. All right, so it's almost 3:15. So well, we have 3:20, right? Oh, never mind. I'm gonna keep going. Yay. All right. Sorry. Okay. So we have alkynes, and so if you just want to get it down to an alkane, just catalyze yourself away. If you want to stop at an alkene, you have 2 choices: a cis alkene with Lindlar's catalyst or nickel boride, or a transalkene with the dissolving metal reduction, sodium or lithium in ammonia. Okay, and they have two different mechanisms. One syn addition at the surface, and the other one has no surface, and so it's going to go a radical anion, and the radical anion gives us a trans alkene. The other thing we can do is if you have an acidic proton on there, you can turn it into a nucleophile, a good nucleophile. We use this a lot in multi-step synthesis. If your starting material has 2 less carbons than your product does, you probably attacked it with an acetyl. So you want to look at the number of carbons. That's why in multi-step, we always look at the number of carbons first to see if we're breaking or making. Okay. So in addition to that, unlike the alkenes where you can form aldehydes, you cannot form aldehydes with alkynes because there's no hydrogen there. So what you end up doing is you always oxidize them down to carboxylic acids, but it clips them right in half right here. And again, when we're talking about multi-step synthesis, if you end up with something with 1 less carbon, then you probably oxidized off your alkene or alkyne and it was terminal, and it turned that into a CO2. I thought I got further along in the other class. I'm like, All right. So radical reaction, okay? There's only 2 things it can do: hydrogen abstraction and addition to a double bond, giving you another radical. Initiation is when you make the first radical, usually with an initiator, light and or heat. Propagation, you have a radical on one side of the reaction, you have a radical on the other side of the reaction. Termination, you have radicals in the beginning and you have no radicals at the end. So that's the way, those are the different steps you have. And then of course, it's a great way to react with hydrocarbons. Hydrocarbons didn't have any reactions up until this chapter. If you had a hydrocarbon, there's nothing you could do with burning. So now we actually can functionalize it to give us a bromine or a chlorine there. And then we can functionalize it more by doing a dehydration and turn it into an alkene. Then you can do even more chemistry. So it's a great step in multi-step synthesis. All right, radical stability. The benzyl radical and the allyl radical are more stable because of conjugation. That means we can get that allylic bromination and keep our double bond. It doesn't have to lose our double bond. Okay, so we can do that allylic bromination. So then tertiaries, more than secondaries, more than primaries. But vinyl and methyls do form. They're not that unstable. So we can form those, okay? So and that's what, a really good thing to do with a methane. You can actually make the methyl radical and make it into a halogen. Yes?
Would you say there were less reactions in chapter 2 about radicals like tertiary?
Well, there's the general mechanism, but then there's halogenation with and without selectivity. Then there's hydrohalogenation, which is anti-Markovnikov's, and then there's the NBS, N-bromo-6-cinnamide reaction. So I think there's only like 4 different reaction types in there, and they all follow the same mechanism. So we have this radical addition of HBr using peroxide gives us our anti-Markovnikov's product. We have regular halogenation, which could be chlorine or bromine. And again, if you have a choice of a secondary or a primary or a tertiary, the tertiary work does faster, and so you're going to have that as your primary. The other thing we did was the NBS. We can do benzylic or we can do allylic bromination. So benzylic because it's faster, because it's more stable. But notice here we have, with the NBS, we can get allylic. And so it forms the radical, it forms that allylic radical, but we keep the double bond. We didn't add across the double bond. Over here with the HBr, we add across the double bond. So that's a different reaction. Okay. So, and then of course, selectivity. Selectivity. If we try to do bromine by itself, you get a mess. You get the allylic product, you get a dibromo product, you get, you might even end up with a tribromo product because you already did the allylic and then you added across the double bond. So it gets really, really messy. So this NBS is a really good selective way to get that allylic. And again, if you have a choice between primary, secondary, and tertiary, Tertiary is faster. That's going to be your major product. And again, Markovnikov's, anti-Markovnikov's right here. Without peroxides, we get the carbocation, which goes in and rearranges. With the peroxides, we don't get the carbocation. We get the secondary radical, which is where the hydrogen is abstracted from, and then we get the bromine at the least substituted side. And I am going to stop there. Okay, so Wednesday we have a quiz on chapter 11, and then we're going to finish up these slides, and then we're going to have another multi-step synthesis activity. Now that you've studied all of your reactions twice. Okay, all right, done. And I'm going to stop sharing. And I'm going to go ahead and stop recording.